Good morning, CP Calculus class. This is Miss G, and it is Monday, April 14th. I hope you all got some well-deserved rest and relaxation over spring break, and that you're all ready to get back to calculus. All right, so today we're looking at section 5.4. It's called Area and the Fundamental Theorem of Calculus. So we're going to start with the definition of the definite integral. And I'll read it, but I'm going to use the picture down here as I read it to show you what I'm talking about in the definition. So let f be non-negative and continuous on the closed interval AB. So here's the function f. It's non-negative because it's above the x-axis, and it's continuous from A to B. Actually, in my picture, it's continuous the whole way that I've drawn it, but we're specifically looking at from A to B. There are no breaks in the graph, there are no asymptotes, there's no holes, there are no jump discontinuities. It's continuous. Okay. The area of the region bounded by the graph of F and the x-axis and the lines x equals A and x equals B. So let's look at that. It's bounded by the graph of F, here it is, the x-axis, and the vertical lines x equals A and x equals B. And so that's really this shaded region right here. That's denoted by the area is equal to the integral from A to B of f of x dx. So we're going to integrate f of x from A to B, and that's going to give us the area under the curve, between the curve, the x-axis, and between the vertical lines A and B. So the expression, the integral from A to B of f of x dx, is called the definite integral from A to B, where A is the lower limit of integration because it's located on the bottom of the integral sign, and B is the upper limit of integration because it's located at the top of the integral sign. Now, what makes this different from the integrals we've been doing before? The integrals that we've been doing before are called indefinite integrals, and you didn't see any little numbers or variables on the integral sign. And also, we won't be adding our plus c. For the integrals we're going to evaluate today, the definite integral is going to have a definite answer. It's going to come out with a numerical value which will represent this area. You see, in geometry, we could find areas of rectangles and triangles and trapezoids because they were all made by line segments and we had formulas for them. And then we could also do a circle and we had a formula for that area. Today, we're going to find areas of integrals. They will also be bounded by line segments, but in the future, next lesson, we will be able to find areas that are bounded by curves and line segments. Okay, so let's get started with today's. Let's see how this works. Evaluating a definite integral using a geometric formula. So we're really going to be using some geometry today more than we're using calculus. But we do have the integral expression. The integral from 0 to 2 of 2x dx. So we start by taking our function, which is 2x, and we're going to graph it. I called it y, but according to our integral notation, we called it f of x in our definition that I just read earlier. So f of x is 2x. We are going to graph this, and I know you all know how to graph the line y equals 2x. So here is that line. If you don't remember how to graph any of the graphs today, just put them in your calculator and you'll see where they go. Okay, so here is that graph. We're going to look at this graph from what numbers? From 0, my lower limit, to 2, my upper limit. So I would go over to my graph, and I would draw a vertical line at 0 from 0 up to the graph. But 0 is already on the graph, so I can't draw a vertical line. But I go to 2, and I draw a vertical line at 2 up to the graph. And then I shade the region between 0 and 2 underneath the line y equals 2x. and bounded by the x-axis. So I'm just shading this. What have I made? I've made a triangle. So since the integral from 0 to 2 of 2x is really the area, represents this area, I don't need calculus to find an antiderivative. I can just use my geometry because this is made up of line segments and it forms a triangle. So what's the area of a triangle? Half the base times the height. So my integral from 0 to 2 of 2x dx, it will equal 1/2 the base times the height. And my base here is 2. And my height is 4. So my answer is 1/2 of 2 times 4, which is going to be half of 8, which is 4. So the area here is really 4 square units. I didn't put units because I didn't give you units, but it's really 4 square units because it's area. And there you have it. We use geometry to evaluate our integral. I'll do one more. Let's look at that same integral as far as the function goes, the integral of 2x dx, but let's look at it from 1 to 2 instead of from 0 to 2. So you would still graph whatever you find here after the integral sign, which is 2x, which we did before, and I just graphed it again. And then at 1, my lower limit, I draw a vertical line from the x-axis to the graph. And then at my upper limit 2, I draw a vertical line from the x-axis to the graph. And then I shade between 1 and 2 and the graph and the x-axis, which gives me this region right here. Now that looks like a trapezoid. So if I want to evaluate this using geometry, I could use the area of a trapezoid. But I didn't use, you see the trapezoid because you have a parallel line here, a parallel line here. And then here it would be your height. These would be your bases. And you could use 1/2 the height times the sum of the bases. But I didn't do that, and you don't have to do that. I just took the trapezoid and divided it into a rectangle and a triangle. And then I'll just find the area of each one of those and then add it together. So my rectangle has a base of 1, because it's going from 1 to 2, that's 1 unit, and the height is 2. So the area of the rectangle would be 1 times 2, plus the area of the triangle, which is 1/2 of its base, which is 1 unit as well, times its height, which is going from 2 to 4. So that height, that height is 2. So the area of the triangle is 1/2 times 1 times 2, which would be 1. And when I add that to 2, I get 3. So the area of the shaded region, which is representing the integral from 1 to 2 of 2x dx, is 3 square units. So we're using geometry. Tomorrow we'll be using a little calculus, but today we're using geometry. Why? Because when we draw our pictures here, our diagrams, we see that they come out to be geometric shapes because they're made of line segments. We have the trapezoid or a rectangle and a triangle here, and then we have the triangle there. All right, so I have a few of these for you to practice tonight, and they come from section 5.4, page 348, numbers 1, 3, and 5. So you're going to do the same thing. You're going to draw the function, and then you're going to draw the shaded region in, and then you're going to use a little geometry to find the answer. If you don't know in number 5 what that graph looks like, put the function in the calculator and graph it and see what it looks like, draw it, and then find the area. You'll recognize it when you see it. Okay? I hope you have a great day and take care.